Electric fields can induce dipoles in insulators. Electrons in insulators are bound to the atoms and to the molecules, unlike conductors where they can freely move. And when I apply an external field, for instance a field in this direction, then even though the molecules or the atoms may be completely spherical, they will become a little bit elongated in the sense that the electrons will spend a little bit more time there than they used to, and so this part becomes negatively charged and this part becomes positively charged, and that creates a dipole. I discussed that with you already during the first lecture, because there's something quite remarkable about this, that if you have an insulator, notice the pluses and the minuses indicate neutral atoms, and if now I apply an electric field which comes down from the top, then you see a slight shift of the electrons. They spend a little bit more time up than down, and what you see now is you see a layer of negative charge being created at the top and a layer of positive charge being created at the bottom. That's the result of induction. We call that also sometimes polarization. You're polarizing in a way the electric charge. Substances that do this, we call them dielectrics, and today we will talk quite a bit about dielectrics. The first part of my lecture is on the web. If you go to 802 web, you will see there a document which describes in great detail what I'm going to tell you right now. Suppose we have a plane capacitor, two planes which I charge with certain potential, and I have on here, say, a charge plus sigma, and here I have a charge minus sigma. I'm going to call this free. You will see very shortly why I call this free, and this is minus free. So there's a potential difference between the plate, charge flows on there, it has an area A, and sigma free is the charge density, how much charge per unit area. So we're going to get an electric field which runs in this direction, and I call that E free. And the distance between the plates, say, is D. So this is a given. I now remove the power supply that I used to give it a certain potential difference. I completely take it away. So that means this charge here is trapped, cannot change. But now I move in a dielectric. I move in one of those substances. And what you're going to see here now, at the top, you're going to see a negative induced layer, and at the bottom, you're going to see a positive induced layer. I called it plus sigma induced, and I call this minus sigma induced. And the only reason why I call the other free is to distinguish them from the induced charge. This induced charge, which I have in green, will produce an electric field which is in the opposite direction, and I call that E induced. And clearly E free is, of course, the surface charge density divided by epsilon 0, and E induced is the induced surface charge density divided by epsilon 0. And so the net E field is the vectorial sum of the two. So E net, I give it a vector, is E free plus E induced, factorially added. Since I'm interested, I know the direction already, since I'm interested in magnitudes, therefore the strength of the net E field is going to be the strength of the E field created by the so-called free charge minus the strength of the E field created by the induced charge. Minus because this E vector is down and this one is in the up direction. And so if I now make the assumption that a certain fraction of the free charge is induced, so I make the assumption that sigma induced is some fraction B times sigma free. I just write now an I for induced and an F for free. B is smaller than 1, If B were 0.1, it means that sigma induced would be 10% of sigma free. That's the meaning of B. So clearly, if this is the case, then also E of I must also be B times E of F. You can tell immediately they're connected. And so now I can write down, for E net, I can also write down E free times 1 minus B. And that 1 minus B now, we call 1 over kappa. I call it 1 over kappa. Our book calls it 1 over K. But I'm so used to kappa that I decided to still hold on to kappa. And that K, or that kappa, whichever you want to call it, is called the dielectric constant. It's a dimensionless number. And so I can write down now, in general, that E, and I drop the word net now. From now on, whenever I write E, throughout this lecture, it's always the net electric field. It takes both into account. So you can write down now that E equals the free electric field divided by kappa, because 1 minus B is 1 over kappa. And so you see in this experiment that I did in my head, first bringing charge on the plate, certain potential difference, removing the power supply, shoving in the dielectric, that the E field will go down by a factor kappa. Kappa for glass is about 5. That would be a major reduction. I will show you that later. If the electric field goes down in this particular experiment, it is clear that the potential difference between the plates will also go down, because the potential difference between the plates V is always the electric field between the plates times D. And so if this one goes down by a factor of kappa, if I just shove in the dielectric, not changing D, then of course the potential between the plates is also going down. None of this is so intuitive, but I will demonstrate that later. The question now arises, does Gauss' law still hold? And the answer is yes, of course. Gauss' law will still hold. Gauss' law tells me that the closed loop, closed surface I should say, not closed loop, the closed surface integral of E dot dA is 1 over epsilon times the sum of all the charges inside my box. All the charges, the net charges, that must take into account both the induced charge as well as the free charge. And so let me write down here net to remind you that. But Q net is of course Q free plus Q induced. And I want to remind you that this is minus and this was plus.